Good afternoon, everyone. I'm really excited to be here to present our work. My name is Coby Wang. I'm a PhD student at UNC Chapel Hill. My advisor and collaborator is Professor Mike Reiter. Today, I'm going to talk about how to end password use on the web. Okay, first of all, what is password use? Password use refers to the case where a user uses the same or similar passwords across multiple websites. According to numerous studies in the past 20 years, most of the people reuse their passwords at different websites. People tend to reuse passwords mostly because they don't want to or find it hard to memorize too many different passwords, which is understandable. However, password use has left a huge time bomb to users' account security. Unfortunately, numerous user passwords have become accessible on the internet. Not to mention tons of data breaches happening in the past decade. These headlines are about data breaches announced in the past 2 months. Up to now, billions of user passwords have been leaked, which is a total disaster. Leaked password and password use together make credential stuffing attacks very effective. During a credential stuffing attack, an attacker could try to log in a user's account at many websites with leaked user ID password pairs obtained from data breaches, phishing, malware, etc. And if one of the users reused the leaked password on these websites, then her account at this website could be easily compromised. For this reason, password use has become one of the biggest concerns for web security. These are some quotes from security people who work for major web service providers, which express their concerns. Existing work include detecting and cross-checking leaked passwords. Also, there are many proposals to defend credential stuffing by setting up two-factor or multi-factor authentication. And there are frameworks out there trying to detect compromised account by setting up hunting accounts or monitoring account activities. A straightforward approach to detect password use is to cross-check users' password on the client side, which, for example, could be achieved by password manager or a web browser extension. However, this approach could be easily circumvented or opted out by users. To the best of our knowledge, our work is the first to actively interfere with password use on the server side. Okay, now let's see the goals we expect our frameworks to achieve. First, we expect our framework to achieve the following functionality. Say a user, Alice, wants to register a new account or to change her password at website A, here called the requester. After Alice submitted a new password to website A, the requester, will be able to check with other websites where Alice already has accounts, here called the responders, whether or not Alice submitted password or its similar variants have already been used by Alice at these responders. With such a password use check, the requester could determine whether or not to accept Alice's submitted password. Of course, if rejected, Alice could submit another password for a new check. For security and privacy, we expect our frameworks to achieve 2 goals. The first is account location privacy. We don't want any of the participating websites to learn at which website Alice already has accounts. The other goal is to improve users' account security by preventing password use, and meanwhile, not to qualitatively degrade account security in other ways. For example, we don't want the responders to learn the new password Alice tried to set or reset at the requester, and we don't want the requester to learn any of the passwords Alice registered earlier at the responders. Okay, now let's see our design. There are 4 key elements in our framework design, which includes a private membership test or PMT protocol as a building block, a directory, a third party called directory, some techniques for account location privacy, and a series of countermeasures to reduce information leakage. A private membership test protocol is a two-party protocol which enables the requester who holds an element P to test whether or not P is in the responder's input set S. At the end of the protocol, the requester only learns whether P is in S, but doesn't learn S. And the responder doesn't learn anything, not even the result of such a test. Okay, to detect password use, when each responder has a password set for Alice, which includes the hash of the password Alice registered earlier and its similar variants. When Alice submits a new password to the requester could launch multiple PMT instances to detect whether or not the submitted password already exists in responder sets. Since existing PMT protocols are not best suited for our framework, we proposed a new PMT protocol design. Our PMT protocol requires only one round of interaction and only one ciphertext in each response message. This could be very helpful in improving performance, communication scalability and performance. In addition, our PMT protocol limits information leakage to only 1 bit, even if malicious parties are present. More specifically, a malicious requester can only obtain up to 1 bit from the responder's input. Such information leakage is actually by design, since an answer to any yes or no question will reveal up to 1 bit of information. A malicious responder could possibly infer the PMT result by observing whether or not the protocol is repeated. For example, if the requester continues to query for the same user, then the responder could guess that the last PMT must be positive, so the user had to submit another password to a new check. To reduce such information leakage, we allow the requester to send a fake query to confuse the malicious responder's observation in a probabilistic way. I won't go into the details here, but in our paper, we briefly introduce this defense. To help the requester find and contact those websites where Alice already has an account, we introduce a third party called directory. The directory maintains what you can think as a forwarding table. This forwarding table contains mappings between user IDs and associated responder addresses. So the main job for the directory is to forward messages to the right party based on the forwarding table, but not involved with any password storage or crypto operation for PMTs. Okay, now let's see how our framework works. First, each responder has a password set for Alice, which includes the hash of the password Alice registered earlier and its similar variants. When Alice tries to register a new account or to change her password at the requester, she submits her user ID along with a new password to the requester. The requester generates a PMT query and sends it to the directory. The directory finds out which website it should forward the PMT query to and then sends the query message to each of the responders. After generating responses, the responder sends the responses back to the directory, and the directory shuffles the responses and send the responses back to the requester. Then the requester decrypts the responses and to determine whether or not to accept Alice's newly submitted password. Okay, to ensure account location privacy, we need to consider 2 cases where a participating website chooses to trust the directory for account location privacy or not. First, if the directory is trusted for account location privacy, then this dash line could be instantiated with normal communication channels. And the responder address stored at the directory could be normal URLs. On the other hand, if the directory is not trusted for account location privacy, then we need to instantiate this dash line with anonymous network circuit, for example, Tor circuits. And the responder addresses stored at the directory should be corresponding pseudo addresses, for example, onion addresses. Tor, the onion router network, enables anonymous communication. In our implementation, we set up a customized Tor network across 8 different data centers in Europe and North America to ensure account location privacy when the directory is not trusted. For security analysis, I will only talk about security against malicious requester. And if you would like to learn more about our security analysis, please read our paper. Some of you might have started to wonder that what if a malicious requester is trying to figure out the responder set by launching a large number of queries? In fact, it'll be hard for the requester to do that because first, account location privacy makes it more difficult to determine the identities of the responders. Second, the directory could ask for users' confirmation to proceed with the protocol. For example, when a query comes into the directory could send an email with a confirmation linking it to the user. If the user doesn't confirm the query, then the directory will hold all queries for this user and drop them if timeout's waiting. On the other hand, if the user confirms their query, then directory could proceed with the rest of the protocol as usual. In our probabilistic model checking experiments, we aim to evaluate how much advantage a best strategy adversary could take advantage of such a password use check. Here, we model the adversary as a Markov decision process. And we model the difficulty of cracking a user's password based on the adversary's prior knowledge about these passwords as a dictionary of fixed size from which user choose their passwords. Okay, we allow the adversary to launch a series of PMT queries and logging attempts at any responder in any order out of her choices. The winning condition for the adversary is to compromise at least one account before she's spending up all PMT and login budgets. We plotted the max probability of the adversary's success in compromising at least one account as the function of the dictionary size, which, again, modeled the difficulty of guessing a user's passwords based on different levels of prior knowledge about these passwords. So this solid curve represents the baseline where the adversary is not allowed to send any PMT queries. As we can see here, when the dictionary size is small, more PMT budgets would bring the adversary higher probability of success. However, this advantage almost disappears when dictionary size gets larger. So in our model checking experience, the plots were all in this long-tailed zucchini shape, which indicates that the best strategy adversary needs a decent amount of prior knowledge to make a difference. In other words, the security degradation brought by such a password use check is limited if users' passwords are not too guessable. For example, at least as strong as a password with only 3 randomly generated characters. Okay, I'll skip the implementation and performance evaluation due to the time constraint. Now I'm gonna talk a little bit about the scalability of our framework. We evaluate the scalability of our framework on our prototype system. If we define the responses returned to the requester within 5 and 8 seconds as the qualifying responses for trusted and untrusted directory, respectively, then each of these numbers represents the max number of queries our prototype system can process in 1 second. As we can see here, the maximum qualifying response rate in the untrusted directory case is much smaller since Tor is enabled. However, as a conservative estimate shows, a throughput of 50 qualifying response per second offered by our prototype system is enough to enable about 300 million internet users in the US to set up or change passwords on more than 5 accounts per year. To sum up, we propose a framework to detect password use and meanwhile to ensure account security and account location privacy. We propose a new PMT protocol as the building block to minimize the information leakage. To the best of our knowledge, our work is the first to actively interfere with password use on the server side, and we believe even modest adoption of a framework could break the culture of password use and improve users' account security on the web. Thanks. I'm happy to answer any questions.
All right, Nick Foragi, Stony Brook. Thank you for your talk. I'm here. Hello. Hi.
Oh, okay.
So have you considered denial of service attacks in your models where you have a malicious service that will always claim that someone's password already exists in their database as a way of stopping that user from creating an account potentially on a competitor's website?
I'm sorry, I didn't understand quite honestly.
So I'm asking if you have considered denial of service attacks, right, where a malicious service will always claim that someone's password is already registered on their website as a way of stopping that user from creating a new account on another website, potentially a website of a competitor.
I'm sorry, I'm sure I'm...
So malicious verifier or requester, if they set the user set to the empty set, or...
Oh, you mean, oh, okay. You mean the malicious responder set the empty set to do like DDoS like attack?
So can a service lie so that it claims that all passwords that a user tries are already exist in its own database, and therefore that password should not be reused on the new account?
Should not reused.
Okay. Well, maybe I'll ask you offline. All right.
Okay.
So I guess like if Facebook said, yes, this password existed, but the password didn't exist in Facebook's accounts.
Oh, you mean it doesn't exist in the responders, but so I think we have a mechanism to detect such a like bad response. Like the directory or the requester could send some like hard bits fake query to find out if the response are responding faithfully.
Okay, so maybe Ben, hi, from CISPA. Is there a constraint on how a password is stored on a given server?
You mean on the responder?
So on a responder. So say I'm Facebook, but I don't store my passwords in plain text, I hope. But I'm using salts maybe. Does that influence somehow the whether this can work or not?
Yeah, that's a good question. So I think that the responders generates its set based on how they define the similarity and how they require this their security requirement, and I think the salt should be like for a user for a specific username, not the salt for the user like one salt for one user ID like that.
Okay, so that means you have to kind of have a way of saying this is similar to some other password. So just using a salt and using MD5 or something, well, SHA-256, will not work, correct?
I'm not sure I understand, but if when you register new account at the website and you submit a password, and the password and the similar passwords are sorted and put in the responder set, and this at the same time, and then so.
The general question is, does the scheme require that that all the hash functions that all the sites use are the same?
Oh, that's right. That I think there's a negotiation going on before, like all the websites participating in this framework.
Okay, thanks.
Okay, thank you.
Abdul from Carleton University. So the focus is to prevent password reuse across services for a single user, but that does not prevent reuse across users, right? So, for example, 10 users could be reusing passwords, except that the passwords are not being reused within the same single user. So I could choose password 1 and then password 2, password 3 on 3 services. Somebody else could also use password 1, 2, or 3, but just in a different order of these services.
Different order, you mean?
Yeah, like on my password on Facebook is going to be P1, on Gmail P2, on YouTube P3, for example, and somebody else for Gmail, instead of P1, it's going to be P2, and then P3 and P4, and so on. So there is still reuse, but it's just across multiple users. So that doesn't, what I was saying is that the password distribution is still going to be skewed, highly skewed, because users are just going to maybe append a digit, add their password, and then their password is different across services, but the password distribution in the services is still going to be highly skewed.
You mean different usernames on different websites?
Yes, yes.
So if I think if the username, so our assumption in this paper is that the usernames are the same. So if you have different, like slightly different username, and the website could be able to infer, could be find out that these usernames belong to the same user, then this work could be still effective. Like every time the user ID could be another kind of ID for the user. But if a website or attacker cannot figure out that this user ID is actually for the same person, then I think it's okay, because you have different user ID, totally different user ID. That's different. Like it's for attackers, that's a different persons, right?
Okay. It's not quite my question, but maybe we could discuss later offline. Yeah. Thank you.
Thank you.
Yeah, all right, we're at time. Thank you.
Okay, thank you.